Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the most awesome stuff. This is the AAS Journal Author Series. And I am super happy to have Jeff Seabrook and Michael Daly with us today. Hey, Jeff. Hey, Michael.
Hi there.
Hello.
And you two are both at the same institution. Is that correct?
That's correct.
We are.
University.
Where are you at?
York University in Toronto. We're with the Center for Research in Earth and Space Science, for which I'm the director.
Very cool. Very nice. Snow on the ground?
There is snow on the ground and more snow coming tomorrow.
Okay. Do you guys ski or ice skate or anything like that?
We're Canadian.
Play hockey?
Skating,
Actually,
hockey,
I do
yes.
not.
Skiing, no.
I don't know. Maybe they had some pickup games outside the building or something like that. I don't know. Let's see. So it is January 24th, 2023. One of the first recordings of 2023 as we do this one. I'm in Phoenix, and we actually got a little bit below freezing this morning. So a little unusual for Phoenix, but we have no snow on the ground. So, oh well. Very good. And Mike, what do you like to do for research?
Well, most of my work over the last 14 years that I've been a professor has been focused on planetary science instrumentation of various types, mostly laser-based, some spectroscopy, but in this case, we're going to be talking a bit of LiDAR, for which I was the instrument scientist on the OSIRIS-REx mission.
Very nice. Very nice. And Jeff, what do you like to do for research?
Oh, a lot of my research has been focused on remote sensing using LiDARs. So constructing instruments, taking them in the field, doing atmospheric measurements, things like that. And then transitioning into the space sciences was working with this scanning LiDAR to map Bennu.
Cool.
So my main interest is in the lab tinkering, basically.
I like that. Very good. Very good. And with that combined set of expertise, that is going to take us to this very lovely Planetary Science Journal article. It's open access. You can go get a copy for free, people. Go grab it. Building a high-resolution digital terrain model of Bennu from laser altimetry data. And Jeff and Mike, take us away.
All right. Well, maybe I'll give everyone a little introduction to the mission and sort of the background for the paper, and then Jeff can deal with some of the details since he did the majority of the heavy lifting on the analysis. So this is an OSIRIS-REx paper. So as I think most of your listeners probably know, OSIRIS-REx was a mission to the asteroid Bennu, which is a carbonaceous asteroid. And I was the instrument scientist for the Canadian instrument, which is the OSIRIS-REx laser altimeter, and Jeff was the deputy instrument scientist.
Cool.
So our job really was, well, there are a number of jobs, but the major job from our perspective and from this paper's perspective was to produce a very detailed global shape of asteroid Bennu. So we did that primarily in the summer of 2019 over 6 weeks. Most of the data that this paper is using was that data set. There was other data as well, but this is the primary data set for us in this mission.
Nice. Okay.
And so one of the things that makes this laser altimeter so unique is it has a very high rep rate, which is a measurement rate of 10,000 times per second. So every 1 second, we took 10,000 measurements of the surface of Bennu.
Nice.
And that was really enabled by two things. I was enabled because we were around 700 meters from the surface of the asteroid, so we needed smaller laser pulse energies than is typical of a laser altimeter that might be orbiting Mars or the Earth or something like that. And then to make this all work, the other thing that makes OLA special is that it has a 2-axis scanning mirror, so a very fast scanning mirror that could take, instead of just sort of spots that we had to put together, it could take sort of cohesive pictures of the surface of the asteroid in 3D.
Nice.
And then we could actually take all those cohesive pictures and using the fact they were, all of the points were well known with respect to the rest of the points in, let's call it an image, we could place those images together and match them and build up the whole global model of the asteroid in a way that hasn't been done on a planetary laser altimeter before.
Nice. Nice.
So that was the plan.
Yes.
And what some of this paper deals with is how the plan didn't exactly happen to plan, which is always happens. That's
research.
Yeah. Well, space mission, it always happens at some level. With a space mission, you think you have it all sorted on the ground, and you launch the instrument, and stuff happens. Either the target is different than you expected, which was also the case for us with Bennu. Bennu was much rougher than we expected.
Okay.
But we also had some still largely unexplained instrument surprises.
Okay.
For want of a better word.
Okay.
Okay, so what happened was we went to plan. We collected all of the data, which amounted to almost 900 of these, cohesive images over Bennu, many, overlapping and often covering up to, I think the typical minimum was 4 overlaps over everywhere on Bennu, and then at the poles it was significantly more, because we took all this data in a terminator polar orbit.
Right. Right.
So we had lots of data, almost 3 billion measurements, which was really cool for us, because
Awesome.
we anticipated early on when I was first putting the plan together that we were going to get something like 300 million measurements. So we got, in this phase, almost 10 times what was the initial thought. So
cool.
we have a wealth of data. And that wealth of data became important in the analysis and the corrections in this paper.
Cool.
So what happened? We built our first model of Bennu, and we were very excited about it, because it was very detailed, and the surprising roughness of Bennu meant we had a huge, a lot of interesting features, and we could see that we were capturing those features quite well, and the instrument was working well. So we built our model of Bennu, and just as a scale, Bennu is about 500 meter in diameter object. So when we built it, we noted that we were a couple of meters too tall at the poles on radius, and a couple of meters too narrow at the equator. And this aspect ratio was kind of enough to see even in the pictures. So we're scratching our heads, wondering, if we were right or wrong, or what was going on. And so we were fortunate we had a couple of ways to check this. There was another way of producing a shape of Bennu using primarily camera-based, so stereo photoclinometry. So it's a camera-based method of producing a shape using stereo and lighting and shading.
Yes.
Which was led by co-authors of this paper from PSI. Maybe I'll just mention our co-authors a little bit while we're here.
Sure.
So Jeff and I were primarily responsible for the laser altimeter. Olivier Barnewin was a significant part of the laser altimetry, but led the altimetry working group, for which I was the deputy. So together we were responsible for the overall altimetry, which included both the laser altimetry and the shape modeling from stereo photoclinometry on the mission.
Okay.
And then Eric Palmer and Robert Gaskell, they were primarily responsible for the stereo photoclinometry. So
Cool.
they were the brains and the producers behind those other models.
Cool.
Hari, he worked with Olivier and helped us a lot on the details of some of the tools associated with producing all of these models, actually. And then Dante Loretta at University of Arizona was, so I may not have mentioned Olivier and Hari are at Johns Hopkins University APL. Yep. Eric and Robert are at PSI, and Dante is the PI for the whole mission at University of Arizona.
Just down the road from me. Yep.
Right. So we compared our shape with Eric and Bob's shape,
Right.
and some images, and whoops, we're wrong.
Okay.
We were too high at the poles, we were too narrow at the equator, and then that started off the process of what is going on here.
Right.
And that's really the kickoff of the whole paper. So if you want to see what the original plan was, you can go back to Jeff, your previous paper was 2019
Yeah,
paper.
it's 2019 paper.
Mm-hmm.
On in PSS,
There we go.
to see how we went to plan. And this paper is explaining how we got back on plan after we got surprised by the instrument.
Okay. Talk about some
So
of that.
that's maybe the start of this. And Jeff, why don't you take over and talk a little bit about how the analysis went to figure out what's going on here.
Sure. Well, since we're here, we're looking at figure 1 right now on the screen. And this is basically an example of 1 day of coverage of the old instrument during a nominal science window.
Okay.
During orbital B. The black outlines are the footprints of raster scans that are taking during the polar
Okay.
orbit.
Mm-hmm.
So in this case, we're progressing from north to the South Pole as the scans were happening. They were taken about every 10 minutes or so, covering a footprint of about 120 by 120 meters on the surface. So you can
Cool.
see that the scans were designed to have overlap,
Mm-hmm.
as you see on the screen right there. So that was by design for these overlaps so that we could get the images basically, as Mike mentioned, pasted together to co-register them.
Okay.
So that's yeah, basically an example of a nominal science window data set.
Cool. Very nice. Very nice. Nans. I like Nans. Very good. I don't see any Nans in this figure, but very good.
There are some NANs, but there are very few.
Okay. It must be in the legend for a reason, but yeah. Very good. Cool.
Yeah, the performance of this instrument was outstanding as far as the data returns at this range. It was it performed superbly. Very few missed observations.
Very nice. Very nice. Okay. Terrain or data filtering.
Yes, so as Mike mentioned, the surface of Bennu was quite a bit rougher than we had expected
Yeah.
during our development and testing phase for this process. We developed this technique and tested it to, I guess, a simulated data set that was quite a bit smoother than what we ended up having.
Okay.
And so a lot of the parameters of the software and the methods we had developed were tuned towards a much smoother surface with less data and a smaller footprint. We originally had a much smaller footprint for our raster scans.
Okay.
So that as we learned more about our ability to control our lack of ability to control the position of our scans on the surface, we were basically forced to take whatever data we got. We had no idea when and where we were going to get data because observations were planned, I think, 8 weeks in advance, and we had no idea where the spacecraft was going to be. So that changed.
No idea, Jeff, might be a little bit of an overstatement, but certainly within the span of a scan, we couldn't predict where we would be on the surface within that span.
Fair enough.
All good.
It did feel like no idea, though.
I think the takeaway from this is that the entire observation set was pretty much planned before the mission phase began, with no ability to change it. So
I'll believe that. Absolutely. All right.
So that did necessitate some changes to our originally planned, I guess, instrument parameters as far as the width and height of the mirror bounds that we were scanning with. And that did have an effect on the data set that we did collect and necessitated some of the recalibration efforts that we had to undertake.
Yeah, there was a positive benefit, and I talked earlier about the fact that we got almost 3 billion measurements, and
Mhm.
some of the reason for all of the ability to take all that data and get it back down, which has resulted in an improved model that's very detailed over what we might have got, was this unpredictability of where we would be when we started taking the data. So just by virtue of having that uncertainty, we actually had to take more data to make sure we had global coverage. So there was
Nice.
some upside.
Yeah, absolutely. Nice. Very cool.
Yeah, so I guess the point, or the overall message of this paper, is that we used key points on the surface to match features. So
Okay.
essentially, we took our three-dimensional data, created 2D images out of it,
Oh,
and ran what is known as a SIFT algorithm on them,
okay.
the scale invariant feature transform key point finder, which basically finds points of interest on a surface and then generates a set of descriptors that describe the gradients of your image around that key point.
Okay.
And using those descriptors, you can um, basically match. If you find two sets of descriptors that match closely, then you can be fairly confident that you've got a feature that matches between different images.
Good. Good.
And that's the algorithm that we use to generate key points in what we call key point pairs, which were matching features on the surface that we used as tie points to register the shapes to each other.
And how many key points were there at the end of
Uh, well, there was hundreds of millions of key points,
Okay.
and through those, not every key point is going to result in a match, but we ended up with a
Yeah.
roughly 60 million key point
Okay.
pairs that were
Nice.
ran a number of filters through them to throw away bad matches and things like that. So we ended up with about 60 million key point pairs that we were fairly confident in.
Cool. Very good. Okay.
Those were used as the control points to both register all the shapes to each other
Right.
and build the shape model, and also to do the mirror calibration that we ended up having to do,
Okay.
in situ mirror calibration.
Let's talk
We,
about that. Why did we have to do a mirror calibration again?
uh, this is gets back to some of the unexpected issues with the instrument that Mike
Surprise.
had described after post-launch.
Surprise.
So at some point between testing on the ground and arriving at Bennu,
Mm-hmm.
characteristics of the mirror changed.
Okay.
The the behavior of the mirror changed in ways that have not been explained yet. And so there was a couple minor issues. One was a bit of noise on one of the axes of the mirror. So we have the azimuth and the elevation axis.
Yeah.
For all of our scans, so that this is selectable, but we stuck with the azimuth, basically left and right from the mirror's point of view, being the fast axis. So that was the part that was scanning
Okay.
quickly. And then, so you're thinking like a line raster scan. So the azimuth, and then up and down was the slow axis. So we would scan left to right really fast and slowly in azimuth up and down to generate our postage stamp of data.
I'm with you.
And in the elevation axis, we found a periodic amplitude noise that was roughly uh, about two Ola spot spacings nominally.
Okay.
So we designed this so that each spot spacing was about 0.05 milliradians apart, but we had this noise along the axis that was about two spot spacings.
Mm-hmm. Mm-hmm.
And so once that was filtered out,
Wow.
that didn't have a huge effect on the data set, but it was noticeable. The bigger issue was we discovered through investigating the reasons for our shape mismatch with stereophotoplanetometry
Uh-huh.
was, well, so this is a long story in itself, but we were basically stumped as to why our shape was mismatched by a couple meters at the poles and a couple meters at the equator.
Mm-hmm.
And we went through a lot of investigations, investigating whether or not the positions of the spacecraft were being represented properly, the velocity of the spacecraft, the any kind of ranging issues with the space or with the instrument, and we eventually narrowed it down to an issue with scaling along the azimuth axis of the mirror.
Okay.
This was, I think, Mike, you had that intuition at some point during a meeting. We had a lot of meetings about this, trying to solve this problem, and I think Mike was the one that came up with this possible explanation, which was a scaling issue in the mirror. So we investigated general scaling in both azimuth and elevation, and we narrowed it down to about a 0.7% scaling issue with the mirror in the
Okay.
azimuth elevation,
Uh-huh.
which
Uh-huh.
is still unexplained.
Huh. Okay.
But once we uh, basically regenerated all 3 billion points with a scaled mirror,
Right.
and then reran the key points through the algorithm that co-registers the
Yes.
data set, we ended up with a shape model that much better closely matched the stereophotogrammetry
Uh-huh.
shape. There were
Okay.
still some small scaling issues on the order of centimeters, but the shape, the overall aspect ratio of the model started to kind of converge. And so we were fairly confident that we were on the right track.
Cool. Very good. Oh, so we have the mystery James Bond factor. 007.
Yeah, I might just add, so Jeff's talking about some remaining issues. I would say once we corrected the 0.7% issue, we performed probably still better than we originally anticipated prior to the mission. So, a lot of what we're talking about in this paper, beyond that 0.7%, are things that corrections we could make and improvements we could make because the capabilities of the instrument were so amazing.
Yeah. Yeah.
The data set allowed us to do it.
Right.
This is, beyond the performance of this was beyond the expectations that I had when we started this, much more than almost a decade and a half ago.
A happy surprise, yes.
Mm.
Always good to have better data than one thinks. Very cool. So let's maybe take a look at images on these corrections and shapes. Here we go. Let's start with figure 2 here. Let's just zoom out a little bit on this one. Figure 2.
Okay, yeah. So figure 2 is an example of what we're talking about by comparing imagery to our generated shape model.
Okay. Mm-hmm.
You can, so on the left is a reference image. Those are images taking a Bennu at various phases of the flight.
Yes.
And on the right are simulated images using the shape model. So you would take the spacecraft ephemeris and generate what the image would look like based on the shape model that we generated.
Yes.
And when you compare the two,
Mm-hmm.
see quite clearly that there's issues at the poles and at the equator where we're a bit squished,
Yes.
I would say.
That's a highly technical term, but yes.
Yeah. We're a bit compressed at the poles and a bit wide at the equator.
Good.
And so these 4 images
Mm-hmm.
are basically just examples of that.
But it's
with our
consistent.
original shape.
It's consistent all the way through.
Yeah.
Independent of the orientation. Yeah. Okay.
So this is what was called OLA version 14, which was our, I think,
Uh-huh.
correct me if I'm wrong, Mike, but this was our first official shape model based on the orbital B data set.
Yeah.
Okay. All right, so we're going to do a correction here. So we have the remove standard deviations. Okay.
Okay, so this is an example of the roughness of the data. I can see a better way to put that
Yeah.
is so one of the metrics we use to determine the quality of the fit of the overlapping data sets
Wow.
was the standard deviation of the radial standard deviation of the points. So if you imagine if you've got 2 point clouds that are overlapping, if they're misregistered and not overlapping properly in any given bin, in this case, I think we chose 20 centimeters by 20 centimeters, you're going to have a high standard deviation in the radius of the points from the center of the asteroid,
I'm with you.
because they're not, certain features are not overlapping properly. So you've got a large distribution of radial distances.
Uh-huh.
And then if you take those points and you match them up together, your radial distribution is going to be much lower. And so your standard deviations in that bin are going to be lower as a result.
Mm-hmm.
So this is an example of basically the standard deviations in any given bin of 20 centimeters by 20 centimeters across the entire surface of Bennu, pre and post
Yep.
scale. Now
Yep.
I would have to double check to see if this is the 1.007 scaling fix, or if this is the full mirror calibration that we undertook.
Yeah, I
Version
don't.
21, I think this is the full calibration.
Oh, okay. This is the V21. Yes.
Yeah.
Oh, this is after.
So I'll just add one. I'll
Uh-huh.
just add one thing here. So what we're looking at here, the standard deviations can't go to zero because roughness is a contributor. So when Jeff talks about the mismatches, it's a combination of standard deviations due to the roughness of the surface and the mismatches.
Okay.
So ultimately there's some non-zero minimum that we could achieve.
Okay. And right. And just to orientate, the tallest feature here is going to be one.
The tallest feature is at about 120 degrees and about minus 45.
Right in here.
Oh, it's the other. Not minus 120, 120. Down on the bottom left.
Oh, yeah.
Right there.
Yeah. Okay, got it. Yes. Got it. Here we
That
go.
feature was about 30 meters
Yeah.
tall, I believe. Ben. So yeah, you can see the high standard deviations around the edges of the boulder.
Right. Even after corrections. Yeah.
Yeah. And that's to be expected because you've got fairly vertical surfaces in a small area.
Uh-huh. Yes. Sharp gradients.
Yeah.
Very cool. And now here we go. This is our key point residuals. Okay.
Oh yes, this is an example of what was done when we were investigating the mirror scaling.
Okay.
So it was a fairly labor-intensive task, which was basically reprocessing the entire data set with a certain mirror scaling in either azimuth or elevation, and then calculating this global standard deviation, and then changing it slightly, recalculating it. So a lot of data processing, a lot of time and basically you find the minimums of using the surface standard deviation to find out your optimal mirror scaling that fixes the issue. So the assumption was that a minimum in standard deviations of the radius standard deviations in the surface would lead you to the correct mirror scaling.
Okay. Just out of curiosity, when you do one of these points and you redo the analysis, what does that take? Is that days, weeks?
It depends how you do it. At first, it did take about 4 days,
Okay.
5 days per data set.
Okay.
But that was regenerating the key points every time I regenerated the data.
Right.
We eventually discovered that just rescaling the key point matches was a much faster way of doing it. So you can imagine that rescaling 120 million points or 60 million pairs was a lot faster than rescaling 3 billion data points and then regenerating all of the key points and matches. So we streamlined this into a much faster process as time went on.
Yes. Cool. Very good.
This process was not in place when the issue came up. We had to basically
trial by fire
as we were going. So
definitely. Well, very good. Congratulations figuring that out. Okay, so there's those, and then we go to the baseline with the deviations removed. Oh, and this is a difference between two sets, yeah?
Yes, this is the difference between the data sets post and pre-calibration. Version 20, I believe, is a shape model that did not have the final mirror calibration at the corners.
Okay.
So there was a number of steps to this. The first shape model V14 had no mirror corrections at all. And I think, I believe still had the noise in the azimuth or in the elevation axis. If that does not ring correct to you, Mike, please feel free to correct me.
No, that's correct. Although that really didn't have any significant effect on the overall shape, which is largely what we're talking about here.
Yeah.
It improved some of the detail.
Yeah, I was just a little hazy on the timeline of that, the azimuth correction. That's all. And I didn't want to misspeak. Version 20 had the 1 point, I think the exact final number was 1.0073
Yes.
scaling factor in azimuth. And in that case, we were still finding some issues with the corners, all four corners of these scans.
Okay.
And so version 20 took our data set and we basically trimmed off the corners of the scans that were showing issues.
Okay.
So once we registered everything and we took a look at basically the distances between the registered data sets and we isolate it by in terms of mirror azimuth and elevation, we saw that we're getting worse results at the corners of the scans. So we trimmed those off to produce version 20. And I think we trimmed off just enough so that we had full coverage of the asteroid. Because if we trimmed off too much, there were gaps. So version 20, we took as much of the corners off as we could. And so it still led to a very good shape model that really closely matched the stereo photoclinometry shapes.
And I think, well, we'll wait till we get to it. I thought that shape model was next, but
so, this is again, this is the difference between version 14 and version 20, and that basically is just another reiteration of the fact that there's a difference between the poles and the equator as far as the radius of the asteroid goes.
Right.
That's what figure 6 is showing.
Right. Forget about it. There's your 2 meter. Difference at the equator and the poles, right? Okay, cool. And we go on, and now 2 different ones, V21 and V20.
Yeah, so this is
the smaller set of corrections, centimeters.
Yes, so this just goes to show that the scaling issue was the primary issue we're having in determining the aspect ratio of the asteroid, and that the final mirror calibration was more of a secondary effect, but was still an improvement.
Yep.
So this is not radius, but just to be clear, this is the standard deviation. So this is not I guess, a 1-to-1 comparison with figure 6.
Okay, got it.
So yeah, I just want to make that clear that it's not a direct comparison. So but it does go to show that there was a fairly decent improvement.
Indeed.
Jeff, you can point out maybe still some scan edge artifacts you can see there that were really the major improvement.
You can see down near Ben where we looked before, where you see the blue.
Yes.
The shape of the blue is the actual shape of a raster scan. So there were some issues with the V20 registered data that were becoming more clear as we improve the fidelity of the shape models we were generating. The small
there's a good example at about 60 degrees and 0 right near go right up. See those sharp edges there are scan edges.
Yes, the corners of the scan right there. So that's popping out of the shape. That's an area of high standard deviation compared to our final version 21 shape. So it's basically highlighting some small defects with V20 that were corrected.
Okay.
So basically showing the need for further calibration. Even though we'd gotten the aspect ratio relatively right, there was still improvement to be had.
Nice. Very cool. Very cool. Okay. And we go on. Oh, and here's another shape model. Okay.
Okay, so yeah, this is a comparison between our version 21 shape and imagery.
Yes.
And so you can see now with this comparison that there's no aspect ratio issues that are apparent at this scale.
Nice. Loves. Yes.
So that just basically a direct comparison to the previous imagery, showing that this was gave us confidence that our shape model was approaching, at
Convergence.
least agreeing with stereophotoclinometry.
There we go. Very good. Cool. And oh, it's some of the key point analysis. Okay. Right. Okay. It's the binning of the key points.
So I think this plot is just showing that where our aspect ratio was correct, we were still disagreeing a little bit on the overall size of the shape. Um, the
Okay.
the OLA shape model was coming in a little bit smaller than the stereophotoclinometry model.
Okay. Right. Okay. Right on those two. Okay.
You have to remind me, Mike. I recall 25 centimeters being something that was thrown around a lot.
Yeah, will maybe just point out that there are some other papers in the focus issue that
Yes.
try and come down and decide which, what the uncertainties are. I might just say that I think we believe the Ola shape model to sort of at the 10 centimeter level and leave it at that. And you can discuss with some of the authors of the other great papers in the focus issue in Planetary Science Journal related to shape modeling, how they did those very sophisticated analyses.
Well said. Well said. Very cool. Yeah, and this image just has sub 10 centimeter resolution. It looks like.
Yeah, this is a comparison between actual imagery of the surface of Bennu
Nice.
compared to imagery generated from the version 21 shape model.
Okay.
Oh, no, sorry, no, that is not correct. This was a small patch of Bennu generated into a 5 centimeter shape model. So the version 21 shape model is not at this high of a resolution, but
Okay.
we did generate very high resolution shapes from the OLA data set
Wow.
over limited areas of the surface.
Wow. 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 Wow.
And so this is imagery on the left versus simulated imagery on the right using the geometry of the OLA shape and the position of the sun to cast shadows.
Good. Good.
So
And
Jeff,
so,
I might just stop you there about your discussion about the global shape model. So the point cloud, the OLA point cloud exists and is self-referenced with all 3 billion points at the global level based on this work. However, if you then take all those points and generate a surface, you end up with a shape model that breaks tools.
yeah.
So I have actually done that, but it is not it is so large and so detailed, it's just unworkable in most people's tools.
Yeah, that's a good point.
So we end up, when we're going down to the finest detail, just looking at a portion of the model.
I understood. Got it.
So yeah, this is a basically key point analysis,
Right.
key point comparison between actual imagery and simulated imagery. And we were trying to get a sense of how well our data set was matching the imagery of the surface and looking at the shadows a little bit to get some kind of sense of our how well we captured the heights of boulders and things like that.
Right.
And so from the cast shadows, you can see that the shadows match fairly well between imagery and the generated OLA shape. So it gave us some confidence that we're capturing things quite well.
At that.
Yeah, I think the other thing that this illustrates, it's a couple things. You're going to come, I think, at the end and ask us about, what kind of work can be done on this in the future. And if you just have a look here at the detail, for instance, that biggest boulder, and look, you can see the sort of the layering. Well, go to the OLA model now, and you can see a lot of surface detail there that's real. And just look at the level of detail of that model and then extend that over the whole of Bennu, including areas of Bennu where we have very poor imagery near the poles because the lighting for the cameras was very, very poor. So we have this over the whole asteroid. So
That is awesome.
there, there's more work to be done with the global model at the large wavelength scale, but here at the the fine detail of the surface morphology and boulders, and you can see fracturing of boulders, and you can see cratering of boulders on top of boulders. The detail here is going to keep many people busy for a long time.
Absolutely. Very cool. Very cool. Science enabling, I think, is what they call that.
There you go.
Very nice. Very nice. And then the article ends off with a couple of appendices on details of the corrections and the polynomial determinations and all that. Do you want to cover that, and just want to mention it?
I think we did cover some of it previously, but yes, this section does go into a bit more detail and show some examples of that periodic noise that we're
Bang, bang, bang,
seeing
bang.
in the elevation, and also goes over the mirror correction that we had to do in situ to kind of correct the behavior at the corners or the extents of the mirror scanning.
Okay.
And this plot here is basically it was looking at how much distance did the corrections fix on the surface of Bennu, just to give you an example of how far a point on the surface would change due to the mirror correction. And you can see as you get to the edges of the scan that some of these points are moving up to half a meter,
Yeah.
which makes a big difference.
Indeed. Very cool. Very good. All right. And for those who want, there's the coefficients on your quartic polynomials. Very cool. Very cool. All righty. The data is available. Do go get it, people. Very nice. All right. Jeff, Mike, thank you so much for walking us through your very lovely PSJ articles, part of the focus issue. Very cool.
Well,
There's an awesome shape model behind you there, Mike.
it is actually, that's V20, so that's not even the best one.
Okay.
I guess that's the point, right? At this scale, you can't tell you can tell the point 073, but you can't really tell these details. But when you get down at the level of looking at a boulder, you can see that there's much better registration. When everything is tied together globally, self-consistent with this much data, to have global registration that works at that level of a boulder, a boulder at this scale, is amazing.
It's awesome. It's wild. So you did mention a little bit as we were going through it, and I just want to probe that maybe a little bit deeper on where do you think we go with this? Let's say over the next 2 to 5 years. We went up to version 21. Will there be a version 31, a version 41? Is there additional data that's in the pipeline that just hasn't been analyzed yet? Just sort of next steps on where we go, besides all of the great enabling of science that people will do with this amazing data set.
Yeah, there's currently no plans to improve on the V21 model, so that should be good to go for analyses.
Right.
We do have some work to do with other OLA data related to the OSIRIS-REx extended mission, which is not talked about in this paper, but some of the other observation approaches that we took in other phases of the mission, we need to go back and look at that data. What happened really was the data we got from this phase of the mission, which is called the orbital B phase in OSIRIS-REx speak, just was so much better that it just sort of superseded anything we had before. Now, we used the other data, and it was very important in selecting, for example, the OSIRIS-REx sample site. However, this data set just sort of overwhelmed it and made it very rapidly not the one to focus on. So for all appreciable science analyses, this data set is the one to use.
Nice. Cool. Very good.
Now, in terms of other work, there's as I said, there's lots of detailed work to do, both at the global and local level all over Bennu. You know, Bennu is only a 500-meter diameter object, but when you get down looking at the level of detail we have here, it's going to keep a lot of people busy for a long time. I know people are starting to look at individual features here like boulders, and you can see layering and you have to pull the data.
Yeah.
And yeah, it's quite an amazing data set, and I would hope that either we or someone will fly an Ola-like instrument to a small body in the future, because this has been game changing.
Okay. I was going to go there, but you went there. Very good. Very good. Jeff, Michael, thank you so much for walking us through this very awesome data set and this very lovely article. Thank you.
Thanks for having us.
Oh, yeah. And that'll do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.